Hi, my name is Ian Fogarty. I'd like to talk to you about carbonyls, specifically about carboxylic acids and esters. Here's a quick review of our carbonyls that we've already started. A carbonyl is a C double bonded to an O, and then whatever is attached over here to this carbon is going to determine what kind of carbonyl it is. We've already talked about aldehydes, where if that would be an H, or ketones, would that be more carbons in our group. And this video is going to focus on carboxylic acids and esters. An OH attached to a carbon-oxygen double bond, that's a carboxylic acid. Do not confuse that for an alcohol where you have an OH attached to just a carbon. That would be an alcohol. No. Specifically, a C double bond O attached to an OH is a carboxylic acid, and it gets the ending oic acid. Oic acid. And again, they're going to happen at the end of chains. Our simplest carboxylic acid is going to be this one with one carbon, C double bond to an O with an OH. And that's going to be called methanoic acid. We know it more as formic acid. Our next one we have is a 2-carbon carboxylic acid, and so it's going to be ethanoic acid, but you would probably know it better as acetic acid or vinegar. And if we look at our line diagrams, formic acid would look like this, just one carbon double bonded to the O and an OH, and here we have 2 carbons attached to the double bond OH. Of 1, 2, 3, so this would be propanoic acid. So 1 carbon, 2 carbon, 3 carbon, 4 carbon, this would be known as butanoic acid. 1, 2, 3, 4, 5, 6. This would be hexanoic acid, but there's 2 of them, so it's going to be something like hexadioic acid. A little bit more about the polarity and the structure of this. Turns out that the electronegativity, here's our lone pairs. Electronegativity of oxygen is 3.5, and there's 2 oxygens. Electronegativity of carbon is 2.5, and the electronegativity of hydrogen is 2.1. So this creates an interesting situation. First of all, it means that the electrons that are in this carbon-oxygen double bond spend more time around the oxygen than they do around the carbon. And the fact that it's a pi bond, a double bond, accentuates that information, that situation. So we have a partial negative there, and that leaves this carbon partially positive. We also have the OH to worry about. And so the electronegativity of hydrogen is 2.1, oxygen is 3.5. So the electrons spend more time around the oxygen. That leaves the hydrogen a little bit electron deficient with a partial positive, and the oxygen with a little bit electron rich with a partial negative. So if we clone this carboxylic acid and come up with an exact duplicate, and if it were to approach, then an interesting thing would happen. You'd end up with a partial positive hydrogen right next to a partial negative oxygen, and so you could have a dipole-dipole interaction or hydrogen bond there and there. And so the carbonyl of one acid could be attracted to the H of the hydroxy group, and over here the hydroxy group could be attracted, H plus could be attracted to the carbonyl. And so this is called dimerization. You have a one thing and another thing, so a 1 is a mer, and so 2 mers make a dimer. This accounts for the high melting point of carboxylic acids. Normally they have a higher melting point than other things that are same molecular mass. Now we know that carboxylic acids have an acid for a reason. They're called an acid for a reason. They're acidic. And so why is that? Well, it turns out that the thing that does the eating, the thing that we associate with acidity is H+, if you're Arrhenius, H+, or H3O+, if you're a Bronsted-Lowry kind of guy. And so what happens is if alcohol were to be acidic, then this H+ would have to fall off and give me the proton, and then this oxyanion. And a carboxylic acid, if it were to become an acid, then this H+ would have to fall off, give me H+, and this kind of interesting situation. Turns out that alcohols are not very acidic, and acids are acidic. That's why they call them carboxylic acids. And so why is that? Because in both cases, you have a hydrogen falling off of an OH, a hydrogen falling off an OH. You have the H pluses and the H pluses, and then this is an OH minus, and that's an OH minus. And so if carboxylic acids are acidic, why aren't alcohols also acidic? And they're not. This does not happen. It doesn't happen very easily. For some reason, this does happen easily. And why is that? Well, it turns out that when the hydrogen falls off, it leaves this bond, turns into a lone pair, and gives this oxygen negative. So we've got 3 lone pairs, it's got a negative charge, and that's great. If that were the end of the story, the acidity of carboxylic acids would probably be about the same as about alcohols. However, one of these lone pairs, it doesn't really matter which, can form a double bond between the carbon and the oxygen to make my double bond down here. The problem with that is the carbon would then have 5 bonds, 10 electrons inside a shell, and it cannot have 10 electrons or 5 bonds inside a shell because it doesn't have any d orbitals. So what can happen is these electrons from the double bond can go onto that oxygen as a lone pair, and I end up with this. The oxygen on the top is still the oxygen on the top. The oxygen on the bottom right is still the bottom right. The only difference is that the electrons have moved. And so this has created a double bond here, and the double bond has broken to become a lone pair. What this means is this negative charge is now shared between 2 oxygens. And because of resonance, this is our second example of resonance. And because this negative charge is shared between those 2 oxygens because of resonance, this is more stable. The hydrogen is allowed to leave because what is left over is stable, and it's stable because of resonance. Whereas in the alcohol, if the H were to leave, you're left with this oxy anion, and that is not stable by itself and doesn't happen very often or very quickly. So the carbonyl structure and polarity is really going to impact our reaction. So this is going to be our first organic reaction. What we're going to do is we're going to take our carboxylic acid right here, and we're going to add an alcohol to it. And what would happen? Now this is going to be acid catalyzed. So we're going to have a container with our carboxylic acid. We're going to add our alcohol to it, and we're going to add a little drop of H+. So this oxygen is electron rich. It's got a partial negative, and so it's going to be attracted to this H+. And that lone pair could form a bond with that H+. And if it did that, it would give me something that looks like this. And this oxygen now has still 8 electrons in its outer shell, but it was only born with 6, and now it has 7, 1 electron here, 1 electron here, 1, 2, 1, 2, 3, 4, 5. Has 5 electrons in its outer shell. It wants to have 6, it's got a positive charge. So this odd-shaped oxygen is really electronegative, and it's pulling electrons in that double bond really towards itself, which means that that carbon is really much more partially positive charged than it was before. Now you got to remember that the alcohol is here, and that oxygen is partially negative, and so there's going to be attraction between those to here. And so this oxygen is going to attack that carbon, but that carbon cannot have 5 bonds, and it's already got 4. If I make another one with that lone pair, it will have 5. So that's okay, because that double bond will break and put the lone pair back on the oxygen, which will fix the oxygen problem. That leaves us with this interesting little structure here, where I have the hydrogen with a OH, no problem. My carbon has 4 bonds here, and then I have my oxygen with a positive charge of 3 bonds. It's still got an octet, so that's okay. But the oxygen with a positive charge is a little bit concerning here. So from an Arrhenius point of view, this hydrogen can fall off. The electrons that make up this bond could reform the double bond, but that would mean this carbon now has 5 bonds, and it can't have 5 bonds because it doesn't have any d orbitals. So it's got to break one of these bonds. Well, it could break this bond right here, and if it did that, then I would end up with the starting product again, and that happens, but it doesn't help us get any further in our reaction. It's not going to break the carbon-carbon bond, because that's pretty strong. It could break this bond, so that set of electrons could go onto that oxygen right there. That would give me this interesting structure, where I have the hydroxide that's fallen off, the H+ that's there, and I have this interesting structure. I still have a positive charge right here, I have a positive charge right there. This newly made hydroxide could then peel that off, put those electrons back on there, and leave me with this interesting thing. And so I've produced my red H plus, my black OH minus, I have my catalyst from the start, and I have this new thing called an ester. This is our first mechanism for our first reaction. So the next functional group is esters. We have our carbonyl, carbon-oxygen double bond, but instead of an OH being here for an acid, or an H for an aldehyde, or more C's for a ketone, we end up with an oxygen with more carbons there. It gets the ending O8. In our mechanism, we showed the details on how the alcohol will attack the carbonyl and produce an ester. Our general reaction is that an acid plus an alcohol will make an ester. The way we name it is the thing that used to be the acid is the parent chain, even if it's shorter, and the thing that used to be the alcohol is going to be the branch. And so here we have ethanoic acid, here we have isopropanol, and so when this reaction happens, the oxygen is going to come in and it's going to kick that out, and that's going to leave me with this beast. The black OH is down here, the H off that is here, and so all the pieces are accounted for. And then we have the thing that used to be the acid with the carbon-oxygen double bond is going to be ethanoate, and the branch that used to be the alcohol is isopropyl. So isopropyl ethanoate. So we'll do the parent chain, 1, 2, 3. So this is going to be the parent chain here, and this is going to be the branch, which gives us 1 carbon in the branch, 3 carbons in the parent chain. This is going to be methyl propanoate. Over here, we want to pay attention to which part has the carbonyl. So this is the acid, used to be the acid, and this used to be the alcohol. The alcohol has 2 carbons. The acid had 4 carbons. So it's going to be butanoate, ethyl butanoate. Ethyl butanoate. Here we have 1, 2. So that's going to be a 2 carbon parent chain, even though it's smaller than this. This used to be the acid, and so it's going to be ethanoate or acetate, either one. And this one is going to be 1, 2, 3, 4. So that's T-butanol is what that came from, which is going to give me an interesting name, T-butyl ethanoate, or T-butyl acetate. Thank you very much for your time.